So what we are going to go over here is how to determine order of reaction. From the reading guide, you should have gotten this equation here. The rate, the speed of the reaction, is based upon a constant times the concentration to a certain power of each reactant if there's two reactants. Gets a little bit easier when there's only one reactant, because then you can get rid of this b to the y part. The key here is x and y are not from the coefficients in the balanced equation. They are found experimentally. So there's two ways that this can be approached. It can be done by a data table, which is what you looked at the book, which we're also going to have on the back side of this sheet that we went over. We'll explain that a little bit. Or it can be done graphically as well. This is one of the big changes that AP Chemistry made to its standards. So what they're trying to have students figure out, they want to add more graphic analysis and less of the plug it into the equations, because I'm sure you saw, for example, if we look at some of the reading, all these equations with natural log in it, or just the concentration, all of these equations used to be used within AP Chemistry. They were ones that students had to simply plug into and solve for something. That is something that the College Board wanted to get away from, and they wanted to move more into figuring things out based upon analyzing data. I'm not going to read these top two paragraphs, but it might be worthwhile if you're confused about this to do it yourself. Instead, I'm going to focus on the three sets of graphs. The graphs are divided into three columns. The first column is the concentration on the y-axis versus time on the x-axis. So that's what all three of these are in the first column down. The second column is the natural log of the concentration versus time for all three. And the third column is 1 over the concentration versus time for all three. What you need to be able to recognize in this class is if you look across, so this is a group across, this is a group across, this is a group across. In each set of three going across, there is one graph that's linear. In the first set of three, it's this one here. In the second one, it's this one. In the third, it's this one right here. One of the things also that you should note about this is that K value from the rate law. Remember, the rate law is K times this times this. That K value is the negative value of the slope, or the opposite of the slope, because it would make it a positive value then. So this is the slope. Only this one isn't actually the positive value. What I would like you to do right now on this sheet is write a big old 0 right here. And on the next row across, write a big old number 1. And the next row across, write a big old number 2. In the lab next week, and then probably on a assessment at some point as well, you need to be able to look at 3 different types of graphs: concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. Whichever graph is linear tells you the order of the reaction. So when we try to figure out what is this exponent here or this exponent there, it's based upon graphic analysis. What will give us a linear change? If the concentration versus time gives us a linear change, that's a 0 order reaction. If the natural log of concentration versus time gives us a linear change, that's a 1st order reaction. And if 1 over the concentration versus time gives us a linear change, that's a 2nd order reaction. Now our textbook again focuses in on equations. But right here is 1st order reactions. And in these equations is natural log. So it actually kind of works. In 2nd order reactions, it's 1 over concentration. Well, what do you know? 1 over concentration versus time is the linear graph. For 0 order, it's just the concentration. So even though we don't need to know these equations from your text, and actually our text then shows this graph right here that's linear, concentration versus time, being slightly aware of those equations does help you identify what I just spoke about. The fact that if we can look at graphs, which is what we're going to be making next week in the lab, whichever graph of either concentration versus time, natural log of concentration versus time, or 1 over concentration versus time, whichever graph gives us linear results is telling us what that exponent is for our rate law equation. Then once you have the slope of that graph, it's telling you the k value as well. This isn't something that I can just kind of have you figure out on your own. It's something I think I had to kind of just flat out tell you. But if you flip to the back side of this sheet of paper, besides looking at graphs, you may have to look at lab data. Now notice in this first reaction, there's only one reactant, A. So that makes our rate expression a little bit easier. It'd just be rate equals K times A to the X power. What we'd want to figure out is what is that order of the reaction. How I would approach this is I would look at the change between time is 0 to 50 seconds. 0.0200 minus 0.0170 gives me a change of 0.03 between those two, right? If I look then at the next time increment, 50 seconds to 100 seconds, that gives me a change of 0.024. If I look at the next time increment, 0 to 150, that gives me a change of 0.022. I'm going to stop there. Does this look like linear change? No. If it was linear change, it would change by the same amount each time. But this isn't changing by that. What I can do then is I know that since this is not linear change, concentration versus time would not give me a straight line graph. Therefore, this is not a zero order reaction. Then, probably not likely that you're going to have to do much of this. I can solve for the natural log of each of these values right here. And I actually did that, so I'm going to just write those down. Negative 3.91 is the natural log of 0.02. Negative 4.07. Negative 4.23. Negative 4.39. The difference between 0 to 50 would be 0.16. The difference from time 50 to time 100 would be subtracting the 4.07 from the 4.23. It's 0.16. 4.23 from 4.39. That's 0.16. That seems pretty much the same value each time, which would mean linear change over time. And if that's linear change, for natural log, this would be a first order reaction. If I were to write the rate law then, rate equals K times the concentration of A to the first power. So what we're working on right now is two different skills. The first one is just look at a graph. Which graph is linear will tell you the order of the reaction. The second one is look at data table to do the same thing. In question number 2, So I'll do one more with you right now. Going from 0.070 to 0.015 would be a change of 0.045. Going from 0.015 to 0.0084 would be a change of 0.0066. After 2 trials, I can tell right away that this is not a linear change. And if that's not a linear change for concentration versus time, it can't be zero order. So then what I can do is take the natural log, the ln. Again, I'll just do it for the first couple of values, negative 2.66, negative 4.20, negative 4.78. If I look at that change, 4.20 from 2.66 would give me 1.54. 4.78 from 4.20 would give me 0.58. Well, that doesn't look linear either. So I can rule out first order. The other option is we could check to see what is 1 over the concentration. So 1 over 0.07 gets me 14.3. 1 over 0.015 gets me 66.7. 1 over 0.0084 gives me 119. And the last one would be 172. If I check the change for each of these, it's all 52. So this gives me linear change. And since it's the 1 over concentration that gave me the linear change, this is a second ordered reaction. What I'd like to do is give you a minute to do questions 3 and 4. Now, number 4 gives you pressure, but notice how I'm giving you the pressure, the natural log of the pressure, and 1 over pressure right away, so no math is required. So why don't you guys right now, and I'll pause the recording for the next day's students, try to do 3 and 4 right now, determining the order of reaction by figuring out, is the change linear over time? What order did we get for question number 3? 0 order. Again, don't be tricked by the 60 to 120 jump. It changes by 0.25, 0.25. This one changed by 0.5, but it's twice as long of a time increment. Number 4, again, is what I think is more likely to happen. I don't think that you're going to have to solve for natural log of these things on a test. I think it would give that to you as an option already. So you really just have to look at which column is linear. So what's the order for question number 4? I had the linear being the one that was natural log, so first order for this one. All right, so that brings us down to questions 5 and 6, which are more similar to that second question on the reading guide. What happens if we have more than one reactant? We have the NO and the H2. If you're doing a problem like this, which is what the practice problems are primarily, if we have time to get to that at the end of class today, so that sheet you picked up on the way in, what you're going to see is usually 3 trials. And what they're doing is they're adjusting the initial concentration of each reactant and then measuring the rate at which the reaction occurs. The key here is if you look at trials 1 and 2, the NO concentration was cut in half. But the H2 has to stay the same then in order to have that controlled variable aspect of it. And I actually prefer in this one to look at 2 to 1. So in trial 2, I then doubled to get to trial 1, my concentration. If I double my concentration, I then look to see what happened to the rate. trial 2 is slower than trial 1 by a factor of 4. 4 times this equals that. So if I double a reactant and it quadruples the rate, that would be second order in terms of NO. Think about it. 2 is the concentration. 2 to the second power equals 4. Now, you could have a problem where they triple the concentration, and then it increases the rate by a factor of 9, because 3 to the second power is 9. Usually in these, they don't manipulate the concentration like that, because then we're just making it more complicated than it's worth. If I look at experiment 2 versus 3, the NO concentration is the same. The H2 concentration, again, was cut. It looks like it was cut by 1.5 here. The rate actually changes by the exact same amount that this changes by. So this would be first order in terms of H2. If I were to write the rate law for this, it'd be K, which I could actually plug in any of these 3 trials values to solve for K, times the concentration of NO to the second power, the concentration of H2 to the first power. It is a coincidence that there's a 2 exponent for the NO, and there's also a 2 for the balanced equation. Again, the coefficients do not mean this, and the proof of that is the 2 here does not relate to that one right there. If we were trying to describe this reaction, we could say it's second order in terms of the NO, it's first order in terms of the H2, or if we add the 2 exponents, it's third order overall. What I'd like to do is have you guys try to do question number 6, where instead of concentrations, it gives you pressures. Same sort of thing. Notice in trials 1 and 2, the PA is the same, but this tripled. What did that do to the rate? In trials 1 and 3, the PB is the same. This doubled. What did it do to the rate? So why don't you take a minute to solve question 6.